This video is on line spectra. So we talked about in our last unit atoms and their particles, protons, neutrons, electrons, where they are. So now we're going to talk about how they behave. So you got to go back to that Bohr model where, right, our nucleus was our protons and our neutrons, and you can see kind of that bare bones drawing on your paper. And then the electrons, remember, are in what we call orbits. Oops, too far. There we go. Okay. So, right, Bohr figured out that the electrons are in orbits. Around the nucleus. Remember, Bohr, it was called the planetary model. Like the sun was the nucleus and the electrons were like the planets orbiting around it. These orbits are also called energy levels, and that's what we're going to refer to them a lot now, is energy levels. And energy levels are numbered starting just outside the nucleus. So in this model that we have right here in this drawing, okay, this would be energy level 1. This would be 2, 3, 4, and if there were more, we would keep going. All right. They have different amounts of energy, hence the name energy levels. So the lowest energy is closest to the nucleus. So lowest energy. And they increase as you go out. So as you go this way, right, they get higher energy. So this, the furthest out would be the highest amount of energy. All right, so electrons are in their energy level, but they can move. They can move when we add energy to them, okay? So when we add different energies, different things happen. So let's talk about what this line spectra is, and I'll come back up to that drawing we were just doing and add to it. So when an electron absorbs a specific amount of energy, so we can add this energy in the form of like heat or light. That's usually what we'll see, heat or light energy. It jumps from what we call its ground state. That's like where it normally lives. So where it is normally. And then it jumps to an excited state. And this will be a higher energy level. Now, when you add energy to something, it gets excited, it jumps up, but it won't stay there. At some point, it's going to fall back down to its ground state. So when the electron falls back to the ground state, that energy that was added is then released. And it can be released in different types of electromagnetic radiation. If it's infrared or ultraviolet or anything like that, we can't see those. So typically, we will only see it, not typically, we will only see it when it's given off in the form of light. Right? So let me draw a picture up here. Okay, so let's zoom in on basically like this. I'm going to take this right here and draw it over here on the right. Okay, so like here's my first energy level, my second, third. They actually get closer as you get farther away. That's why I'm drawing them like this. All right, and let's say my electron is red. Let's say it starts right here. So here's my electron. So this would be its ground state. Right, so here's where it lives normally. All right, but if I add energy to it, if I add energy, so maybe I heat this up, I use some light or electricity, I add energy to this electron, it's going to jump up to a higher energy level. Let's say it jumps up to 3. And so now it's here. When you add energy, it jumps up there. This is now its excited state. But remember, it can't stay there. So at some point, it's going to fall back down. It could fall back all the way back down to 1, or it can fall back down to 2. It can fall back just to any one lower. It doesn't necessarily go back to its original spot. But the key is that when it falls back down, that energy that was added is now lost. So now it loses energy. And if it's the amount of energy in that visible light range of the electromagnetic spectrum, we may see that as light. All right. So what we see is, well, actually, let's go back here. So when the electron or energy is absorbed is when it's going up to a higher energy level, and then energy is released when it goes down. Okay, so this line spectra, okay, this right here is key. A line spectra is when you can only see certain colors. So if you have a diffraction grating, kind of like a prism, where it's going to separate all your different wavelengths, you're going to see different colors. So a line spectrum, you might see just like a blue line, maybe a green line, and then a big gap, and maybe a red line. So it's going to be like the individual wavelengths that together might make one color, but separated out, we can see what the individuals are. And remember, each color is a different wavelength. So this is showing you have energy in like this region, right? Blue, some green, and some red. So you're going to have those different waves. Okay. So elements produce line spectra, and it's different for each element. Think about why that would be different, right? Elements have different numbers of electrons in different locations. They're in different energy levels, and they're going to jump and fall to different spots. So each time that happens, you're going to get these different colored wavelengths. So a line spectra is only individual colors versus a continuous spectrum is when you get all the colors. So this would be like white light. Like if we take white light and we use a prism, right? You're going to see a whole rainbow versus a line spectrum where you're only going to see certain colors. There will be gaps. So know the difference between these two. All right. So white light produces a continuous spectra. Okay. And then, like I just said, light corresponds to a certain wavelength, which then is a certain color, right? The longer the wavelength, the more it is on the red side versus the violet side. So that is line spectra.